How to design a push-pull power amplifier circuit with Sziklai Darlington BJT power transistors at the output is discussed in this example. At the output, we want to deliver a sizable power, 50 watts for example, to an audio system speaker with a resistive load RL of, let's say, 9 ohm. This power amplifier is implemented with one op-amp or operational amplifier, and we have also a Sziklai PNP-NPN transistor pair to push the current, and we have a complementary version NPN-PNP Sziklai pair as sort of our variation of or variant of the Darlington pair to pull the current. So we are designing a push-pull power amplifier. We also have the current limiting PNP and the current limiting NPN BJT transistor that they rely on the proper selection of Rx in this circuit, so that, or sometimes referred to as RCL, current limiting resistor, so that when at the proper time these current limiting transistors turn on to protect, but by limiting the current or output current to protect these expensive power transistors at the output. We also have the series of R1 and R2 as our feedback resistors in this circuit that in combination with the op-amp and negative feedback, they properly set the voltage gain in the system. So we want to find the value of resistors and the proper choice of components to get the power amplifier deliver 50 watts to the output. How does this circuit work? How can we design these components to achieve the 50 watts example delivery of power? At the input, we have a sinusoidal voltage Vin with a proper frequency. Let's say if it is an audio amplifier or power amplifier, then we are talking about 50 Hertz for frequency, not omega, up to say 20 kilohertz. Of course, omega is just 2 pi f, and this is in radian per second, and this is just f. So that omega is properly in the proper range so that we get this sort of a frequency range. The amplitude is something that depends on a specific application. In this case, let's assume that A is 1 volt. That's what is the meaning of that? It means this peak is 1 volt and negative peak is negative 1 volt, but it can be other numbers depending on your application. Let's focus, before getting into more details about the op-amp, let's focus at the 50 watts at the output. So the power of the load is, I'm going to write it here, the power of the load is 50 watts. That's the desired power. Of course, you can see that op-amp is in negative feedback configuration because output of op-amp is connected to the negative terminal, and when input is trying to rise, then output tries to increase as well. So during the positive cycle, we have output rising, and then via the voltage, let's say division between R2 and R1, then we also have this negative terminal rising as well. So op-amp is clearly in negative feedback configuration, and because of that, whenever sinusoidal voltage is at input, we have sinusoidal voltage at the output as well. So, and because we have a resistive load, then voltage of load is, because of Ohm's law, is RL times the current of the load, and the current of the load is this current. So if you have a sinusoidal voltage for the load, then current is sinusoidal as well. So going back to the power, for sinusoidal signal, the power is 1/2 then load times the max load current squared. And by load current, I'm talking about a sinusoidal current that has a peak of IL max, and of course, so this peak is IL max, and this negative peak is negative IL max. Okay, so we want it to be 50 watts. Load is 9 ohm, so RL is 9. Obviously, this results in IL max or peak to be 10/3 amp. Okay, so we found the peak value of the current, so 10/3 amp. Now we also have the Ohm law, so obviously VL max, basically I'm talking about for the load, the sinusoidal signal has a VL max and negative VL max. So that VL max or peak is obviously load times IL max. So with the load of 9 ohm, then VL max is simply 9 times 3 over 10 over 3, which means 30 volt. Okay, so we found the peak. The peak is for the output is 30 volt. So as a practical design, since output at this node, basically at the common emitter of the power NPN and power PNP transistor, if at this node we are having this sort of a signal, then maybe it's a good idea to have Vs to be 35, let's say, volt, as if we have 5 volt margin, and then for negative Vs we have negative 35. So it's a dual supply design, and we can see that the op amp is properly biased by having the positive negative supply of the op amp connected to the positive negative rail, so it's a dual supply design. I can say as a result, op amp is with proper bias, and also as I mentioned earlier, from the output via this wire going back to negative terminal, and as I explained, it felt like a negative feedback, so op amp with proper bias and negative feedback is in linear region, not saturated, and because of negative feedback, it enforces virtual short for the op amp that is operating in linear region, which means voltage of positive terminal is equal to the voltage of negative terminal for the op amp. So if at the positive terminal we have Vn, and for a good op amp we can make the assumption that practically input current is 0, so we don't care about this resistor R, there is no voltage drop, it's just there for the impedance matching. This Vin appears exactly at the positive terminal, and because of virtual short, op amp with negative feedback enforces that Vin also appear at the negative terminal as well. No current can flow through the input of the practically good op amp. Therefore, we can assume that R1 and R2 are effectively in series. So whatever current that goes through R2, because of KCL, when we get to this node, it will have to go through R1 as well. And we can see output via this wire. So output voltage via this wire is exactly at this point. So Vin at this node, or basically Vin at negative terminal, is just the result of a voltage division between R1 and R2 from Vout. So I can say, using KCL or Kirchhoff current law and KVL, Kirchhoff voltage law, basically circuit laws, I can say Vout is simply 1 plus R2 over R1 times Vn by just looking at the situation that I have here, between Vout, Vn, and the voltage division between R1 and R2. Basically, we can say this op amp, the way it's connected, is in a non-inverting amplifier topology. So non-inverting amplifier for op amp. Okay, so what's the benefit? Well, I just found the output voltage to have a peak of 30 volt. I was given that A amplitude of Vn is 1 volt. So therefore this guy is 1 volt in the example. Vout is 30 volt. So using this I can then say, therefore 1 plus R2 over R1 should be 30 divided by 1, and therefore we have 30. So I can say R2 over R1 is 29. Let me write it here. So R2 over R1, maybe over here because I'm going to select the value of R2 and R1. R2 over R1 is 29 if, for instance, we select R1 to be 1 kilo ohm, I'm not saying it's the best choice, I'm just saying as an example, then R2 will be 29 kilo ohm. Okay, so we found the proper selection or proper value, potentially good values for R1 and R2. Now the next step is selecting the value for, say, R3 before getting into conversation about the transistors. So for R3, I need the value of R3 to be set in such a way that when, let's say, IL is 0 in the absence of load, so let's say there is no load, load is removed, let's say, and basically open, so output current is 0, let's say. As a result, we are at, let's say, quiescent point or just bias point. It's I just need enough voltage drop across R3 with the just a quiescent DC current of the supply for the op amp. Say op amp is having 10 milliamp, depends on what sort of a op amp we select. This op amp doesn't require to be a power op amp because the main task of delivering load in push and pull, let's say delivering current or sourcing or sinking current, is done by these power transistors, not by the op amp. So if 10 milliamp is the, let's say, nominal DC bias current for the op amp, I just need enough voltage drop across R3 so that this combination of series of RE and let's say emitter base of, let's say, if this is T1, T2, then it's just about to turn on. So if emitter base require about 0.7, maybe as an example, I can set the default nominal voltage drop across R3 to be 0.7. So in some application, maybe we need to set that to 0.6. It's just a matter of how much potential, let's say, dead zone we can tolerate in this system, because we want this to be a class AB push-pull amplifier. By class AB, I mean we want the transistor, let's say PNP here, T2, to be on the verge of turning on. The same thing about this transistor here. We want it to be on the verge of turning on, so we need plus minus 0.7 volt across, or close to 0.7 across its base emitter, so that it's ready to turn on. Otherwise, we will end up with a slight dead zone, basically in the voltage, in the zero crossing of the output, which increases the THD or total harmonic distortion, which we want to minimize, basically minimizing nonlinearity. So let's set R3 times 10 milliamp in this circuit to 0.7 volt, so that we have this transistor on the verge of turning on, or this transistor on the verge of turning on, because that also depends on the 10 milliamp passing through R3. So if that is the case, then we get that this is 0.01. So what we get is R3 is roughly 70 ohm. Okay, so that's R3. Then for RE, it all depends on what we want to do. In some design, we can just say RE is 0. So basically, we have no resistor here. In some design, we might desire some minimal RE, so that we end up with about maybe 0.1 volt drop across this RE. It all depends on, again, the kind of design we are targeting. So from there, we can find the value of this guy. If we want, let's say, 0.1 volt. How? Let me go back to the output now. So we found the current at the output to be 10 over 3 amp. So basically that means the peak of the current, as I showed here. Let me change the color so that it's obvious what I'm talking about. This current. So we found the output current to be a sinusoidal current with 10 over 3 amp. In this power transistor scheme inside the Sziklai transistor, these guys are sizable power transistors that they are trying to deliver 50 watts of power to the output. I'm going to show you potential choices for these transistors, but basically it means usually the beta of these guys, or the current gain, is pretty low, on the order of say 10 to 20 to 30. So let's say 20. And on the other hand, the beta for this transistor, that is just the average transistor, is on the order of say 100, and maybe this guy even 200, which we don't care that much about. So beta is just the default current gain of transistor, which is just IC over IB, the current of base over the current of collector over current of base. So if we have IL equal to 10 over 3 amp, which is roughly 3.33 amp, then divide by 20 so this current, and this current is mainly provided by when it is being, let's say, sourced, is coming from this transistor, and if the current is being is the sinking mode scenario, then is being actually supported by this PNP transistor. So if we have IL 10 over 3 amp, then this current will be 10 over 3 divided by beta 20. So that means that it would be 1 over 6. So I'm going to write here, this current is 1 over 6 amp, because beta is 20. So that then this current is 10 over 3 amp max. And of course, this current is negligible from perspective of this analysis, because we're talking about 30 kilo ohm resistors here. And also, the current coming from the output of op-amp is not a concern for this analysis, because what op-amp does beyond the DC current of 10 milliamp, op-amp just adds a small AC current that goes like this, while the actual AC current is coming out of the NPN transistor in the, let's say, push mode when we are sourcing the current. In the sinking current scenario, op-amp actually add a current like this, a small signal current, very small, but the main current is actually being pulled in the sink mode by this PNP transistor. So we need to have that in mind. Okay, so 1 over 6 amp for this transistor, and that translates to, with a beta of 100, that translates to, so this one is 166 milliamp. So beta of 100 translate to 1.66 milliamp here, which is very small, and that's reasonable. That's the highest amount of current, because we're talking about the peak current values. At peak current value, this current is 1.66 milliamp. During nominal operation, T1 is not supposed to turn on, because that's the current limiting transistor, and that 1.66 milliamp easily handled by the op-amp that has a 10 milliamp nominal DC current. Okay, so this is the discussion about the situation for the current. Regarding Rx, let's say we want to limit, so I'm going to talk about transistor types, but regarding Rx, let's say to select Rx, let's say we want to limit, let's limit the, depends on again what type of transistor we have selected, but let's say we limit the output current, since we don't need more than, in this example with the 9 ohm resistor, to deliver 50 watts, we don't need more than peak current of 10 over 3 amp. Therefore I can say let's limit the output current to 4 amp. Okay, so that means when we have 4 amp going through Rx via the collector emitter of NPN transistor, or through this Rx via the emitter collector of PNP power transistor, then the voltage drop across Rx with 4 amp passing through it should be large enough to start turning on T1 or to start turning on, let's say, T6 here. To start turning on, we need emitter base of roughly 0.6 volt. Start turning on, basically, not fully turn on. So what I can say is voltage of emitter base of T1, set it to 0.6. It's a PNP transistor, BJT, so, and it's a pretty low current one, 0.6, and I need it to be equal to Rx times the limit of current, which is 4 amp. So Rx times I max. And in that case, this becomes Rx times 4 amp. And because of 0.6 volt that we have here, from here we get Rx needs to be 0.15 ohm. It's a power resistor because it's a sizable current of 4 amp that is passing through Rx. But we found it, basically. That's how, for example, we can set the value of Rx. Okay, so we talked about the value of R3, Rx, and Re. The only thing that remains to be discussed is then the choice of, let's say, potential choices for the transistors, especially power transistors and also op-amp. So in that regard, for the power transistor, one example, there are many options, of course. One example is from onsemi or onsemiconductor, and you can see that the BD243B or 243C NPN type and BD244B and C PNP type, these transistors can be easily purchased from Mouser or DigiKey, and you can see they can tolerate a good, let's say, maximum collector emitter voltage, and also very good power property, 65 watts, if it is properly, let's say, if you have proper heatsink for this transistor. So this is a good choice. And the reason we need to be careful about collector emitter is when we selected the dual supply 35 and minus 35, the worst case collector emitter that can happen for these transistors is about 70 volt. So negative 35 volt plus 35 volt. If the output really goes to lowest level, which is negative 35, it never gets there. Then we have 70 volt across this guy, collector emitter. And also about this PNP as well. If the output goes to absolute highest 35 volt, then we have plus minus worst case 70 volt across this guy. So we better select a transistor that can easily handle collector emitter or emitter collector voltage of more than 70, and this guy can do that. Okay, so, and the current of course is good enough for us because it says 6 amp and we just need about less than 4 amp. So that's about the power transistor in this circuit, in the Sziklai pair. The Sziklai pair, again, it refers to PNP-NPN combination, or let's say the NP-NPNP combination. So that's the difference between Sziklai and Darlington pair transistor. Now for the smaller transistor, we can go with, let's say, by smaller transistor I mean for the second transistor, the smaller one in the Sziklai pair, the PNP on top and the NPN here. We can go with, since we just need 166 milliamp max current for the collector current, then we can possibly go, as an example, there are many options of course, we can possibly go with say, there are many options again, but with a lower transistor that could be, let me see if I have an example for it or not. I don't have an example on hand right now, but but there are many options again available to be purchased. And finally, for the if we would have gone with Darlington instead of Sziklai, of course, these complementary silicon from BJT from onsemi would be good one, but these are purely Darlington pairs, not the Sziklai pairs here. So this is not applicable to this example directly, but a variant of this example can use these transistors. Now, For the op amp, this could be a good choice. There you go. Let me shift it up. So this is an example. There are many choices, of course, but an example of the good choice for op amp, or possibly a good choice for op amp, is this one, OPA 452 and OPA 453 from Texas Instruments, and that would be an op amp with, say, very wide supply range, for example plus minus 40 volt, so it can easily handle the plus minus 35 volt that we have in mind. So it has the plus minus 35 volts that we have in mind in this example. And also for the output current, we just need about 10 milliamp or so, on the order of 10-20 milliamp from this op amp, and it can easily handle that as well. This op amp can, I think it can support up to, there you go, high output load 50 milliamp continuous, so it's good enough for us. Voltage wise and power and the current wise is good enough for us. This is an example of an op amp. There are many options for given the expectation of for this op amp in this circuit. I hope this example is helpful in terms of showing how we can use a combination of sort of a good regular op amp, let's say audio op amp, if it is audio application, with a Sziklai power transistor pair or Darlington power transistor pair in another variant of this circuit, and with current limiting transistors, to actually end up with a higher power delivery at the output using current boosting transistors basically. So this op amp alone could not do this. Combined with this push-pull design, we are able to achieve the 50 watt power delivery to the output. I hope this example is helpful. Thank you for watching.